Hello again. This bit is about a second construction of fields and industrial construction via fields of fractions. The model situation for this construction is integers, the ring of integers being a subring of the field of rational numbers. And the construction really axiomatizes, makes it general, the passage from integers to rational numbers. So if we look into what rational numbers are, well, we can think of them as pairs of integers x over y. And it's loosely a pair of x and y, because a really rational number is not just a pair, but a pair up to certain equivalence. We can multiply both the numerator and the denominator with an equal number, and the rational number that won't change, but this will. So let's start with this situation like that, a ring, and then let's look at the field containing it, and let's seek the smallest one, because rational numbers is really the smallest field containing the integers. So the smallest field containing the ring R. Well, just a second on diversion, not really diversion, on input of this construction on the ring R. So we want it to be sitting inside a field. Not all rings can sit inside fields. Not all commutative rings. The obvious restriction is that R should not have zero divisors, because there will be zero divisors in a field, and that would be a contradiction. So R is a commutative ring without zero divisors. Well, the model example we have, the integers, is such a ring. So then we will just proceed as in here. We will record the elements of our new extended ring as pairs first, and then really as equivalence classes of pairs. So again, elements will be equivalence classes of pairs. Let's just write down this equivalence relation, which would make the rate of x over y and z over w the same. Well, of course, we know how to deal with that. We can translate this equation of rational numbers into an equation of integers. Xw will have to be the same as zy. So that is the definition here. The relation is defined if and only if we have this equation true. The first exercise for you is to check that this is an equivalence relation. To be an equivalence relation, it has to satisfy three properties. You, of course, remember what they are, so please go and check that they are true for this relation. And all you really be using is just a multiplication in the ring R. So really all the three conditions for the relation will have to come from just the axioms of the operation of multiplication. So okay, now we can define the set to be the set of pairs with x and y being elements of R under this equivalence relation. Set of pairs, the set really of equivalence classes on the set of pairs. So I left the gap here to put an extra condition on the elements in a pair. I'm going to build a fraction, a rational element built out of elements of R, and for that sake the denominator should not be zero. So that is the definition of this extension as as a set. Let's make it a ring. Let's define the addition and the multiplication on fractions, but written as pairs first. So we have two pairs. They're both with the condition that the denominators are non-zero, and then we want to add them. The good guiding principle is to look at what happens with these pairs written as ratios, and the basic knowledge of how to do arithmetic with rational numbers would tell us the answer. The denominators will have to be multiplied, the numerators will have to transform under this rule. And so that is the result, that is the definition of addition operation. We just say that the sum of two pairs has to be written this way. The condition that the second coordinates are non-zero is stable under this operation. Moreover, this operation, which is as written is an operation on pairs, is nicely compatible with the equivalence relation. In a sense, it is descends onto equivalence classes. So here is the next thing to check, the formal exercise, compatibility. With the equivalence relation. So really it's an operation on equivalence classes. Similarly for the multiplication, even easier for multiplication, because when we multiply rational numbers, we just multiply numerators and denominators. And again, the condition that the denominators are non-zero is stable. On the same task, compatibility with the equivalence relation is to be verified. So we have a set with two operations of addition and multiplication. Please check that these operations make it a ring. But even better, these operations will be making it a ring which is a special one, still commutative. So R was a commutative ring. But it will also have division. We can say that xy inverse is equal to yx. Well, for that to work, x should be non-zero, because that would be the restriction necessary for this pair to be an element of QR. But that is, of course, automatic, because only non-zero elements are invertible, so that should not be zero element in the ring of rational numbers from R, in R. And of course this means that this is not, say, equal to 0, 1, because that would be the code for the zero element. You can check it by verifying that that works as a zero element for this addition. So everything is in order, that becomes a field. Again, I will make it as a formal exercise, so QR is a field. Moreover, that is a solution, the unique solution for this task, for finding the smallest field containing R. That will be the smallest field containing R. Well, we can postpone verification of that till later. What I'm really eager to do is an example. While we have the model example, which is already here, integers, if we apply this construction to them, this field of fractions construction to the integers, we will get the field of rational numbers. Let's look at another class of rings which are very close to the ring of integers in their properties, namely rings of polynomials. So we'll start with a field F. I'll attach a variable t to it, and that is the notation for the ring of polynomials in the variable t with coefficients from the field F. As the ring of integers, this is the ring without zero divisors. This is what the commutative ring without zero divisors. This is what is called a domain. So it is a valid input for our construction, and the result of this construction is called the ring of rational functions, or rather the field of rational functions. So that, by the definition, is the set of pairs under this equivalence relation. Instead of writing them as pairs, we can write them as radius, where f of t and g of t are both polynomials with coefficients in our chosen field, capital F, and g is not zero. So that will be our second class of examples for the fields. I'll stop now.